It would be much harder to be a good parent. All right, guys, so here we go. Hey, so what we're going to do is we're going to, oh boy, my watch battery just died. So, guys, what we're going to do is started about weak titrations, but what I'd like to do is I'd like to frame this in the context of what we learned about strong titrations. So guys, it kind of goes like this. Familiar, right? So let's talk about the familiar pieces of this so that we can then bring in weak titrations. So first of all, we know that this is a strong titration because they told us that this is 0.1 molar HCl. And if they had just told us that this is a 0.1 molar acid, what would then tell us that this is a strong acid? You better know this. The pH. Guys, this is the pH before we've added anything to it, and that pH is 1. How does this connected to this tell us that this is a strong acid? Well, what's 0.1? So 0.1 in exponential form is 10 to the negative first. What's the negative log of that? 1. That's the idea. So guys, if you have a 0.1 molar solution and the pH is 1, that's got to be a strong acid because it has to be fully dissociated in order for its pH to be 1. Does that make sense? Okay, so with that established, here are the other things we talked about. We talked about calculating the pH initially, and we said pH is the negative log of the concentration of the acid, again, because it's a strong acid. Then, guys, here, in order to calculate the pH before equivalence, this was the part that Austin first mentioned he liked, and all of you agreed. It's just simply convert to moles, do the subtraction, divide by the adjusted volume. That's your molarity. Take the negative log. Yes? Okay. Then, guys, at equivalence, the pH is 7. And then beyond equivalence, the thought process goes the same as before equivalence. Convert to moles, do the subtraction. Now you have an abundance of hydroxide in this case. Divide by the adjusted volume, figure out the pOH, and go from there. You good? Does that all ring and true with you? Okay, so guys, if that is ringing true, what I need you to do then is make sense of the top line in the thing that I just gave you. Notice the header, if you will, on the far left. Strong acid-base titration. And then notice across the top we have those 4 regions. Initial, before equivalence, at equivalence, after equivalence. And then this is the way I said what we just went over. To find the pH, and this is all about finding pH. To find the pH, initially, it's equal to the concentration of the initial solution. Before equivalence, it's equal to the concentration of the unreacted ion. That is found by subtracting. And remember your volume changes, and then take the negative log. Do you see how my words are supporting what you learned about in homework? Then, guys, there's our big 7, right? And as Brandon pointed out, you don't have to do the math to verify that, but you do at least need to conceptually say in a strong acid-base titration, the pH at equivalence is 7 because the product salt, by definition, is non-reactive towards water. Is that jiving? And then, guys, finally, you will notice that after equivalence is the same as before equivalence. The only difference is now you have an abundance of titrant, in this case, as we've been thinking, the base. And so the subtraction just provides or produces an excess of hydroxide. Again, divide by the adjusted volume, you get the idea. You guys good on all of that? Okay, so what we're going to do then today is move down here. And we're going to talk about the equilibrium or the pH of a weak strong titration. So guys, to do that, what we're going to do, and I know that this chart is now going to be distracting. Guys, if you can't stand it, flip it over. Because I don't want you looking at this, because you're going to look because you guys are so fixated on words and you're going to forget to learn. So if you know that you don't have the willpower to not look, get rid of it, because we're going to do it a different way. And then I promise you, we'll come back to it and we'll make connections. But guys, let's do this conceptually first. So what we're going to do is this, and don't do it yet. We'll do it together in a minute. Uh-oh. Why doesn't this work now? Because switching to my new computer no longer, could you pretend like you can see that? No, it's driving me nuts. I got to do this. Okay, hold on just one second. Mouse, smart zoom. Wait, no, that's not what I want. More gestures. Do you guys know how to make zooming work on one of these things? Yeah, but double tap just zooms you in. I wonder if it's under trackpad. Oh, here. Scrolling, pinch in and out, smart zoom. But this isn't relative to my mouse. But do you see anything about zooming? Where? It feels like there's something, no. All right, guys, we're just going to have to pretend. I don't want to spend a bunch of, and I am going to show you a bigger well, here, I've got a bigger one of these. We're going to have to jump back and forth, guys, but let me just let this marinate with you for a minute, and then we're going to talk details. So, guys, notice in blue is what we looked at previously. This is our strong acid-base titration. We've got our 0.1 molar HC. I did not touch that. I might have spit on it, though. It should be. Yeah, but I think we're okay to look. This is big enough. So, guys, here's what we've got. We've got the strong acid-base titration in blue, which is what we've talked about previously. But now what we've done is we have superimposed over this another titration, obviously the one in green. And I'll just tell you right now, this is actually the titration curve for 0.1 molar acetic acid, again with 0.1 molar sodium hydroxide. So what I'd like to do is I'd like you the opportunity to notice the differences. And then we'll talk about why. So guys, how is green different than blue? What are you seeing? Yeah, so the starting pH is higher, right? So why? Why would the starting pH be higher for our acetic acid if its molarity is the same? Yeah, it's a weak acid. It doesn't fully dissociate. We'll talk in a minute about what to do with that. Just a second. We'll talk in a minute what to do with that. But right now, guys, you just got to understand that we wouldn't expect a weak acid to have the same pH as a strong acid at the same molarity because it's weak and it doesn't break apart as much, so its solution is less acidic. Go ahead. Yeah, ooh, we even use the word concavity. We're not going to explain it yet. Well, I'll tell you, but we're not going to understand it. Did you notice that? Guys, that when we add the base to the strong acid, it climbs linearly. But when we add the base to the weak acid, it actually spikes and then becomes linear. Here's what's happening. You'll notice that eventually this becomes linear, right? What's happening in this region is the system is actually self-buffering. I know that doesn't make sense, and it shouldn't, but it will when we start doing this for real in lab. But guys, what's happening is initially the pH jumps rather rapidly, but then eventually what happens is this system buffers itself. And I don't want to say anything more than that, so don't ask. We'll talk about it later. But understand, it's not a life or death issue, but understand that what is actually happening is these systems are self-buffering. And we'll talk more about that, not now. So, what else do you notice as differences? Go ahead.
I have a question about the, I guess the strong acid, but you said it's linear.
Uh-huh.
How is that if pH is log?
That's a good question. So why is the pH increase logarithmic or linear?
The concentration of H plus is decreasing linearly.
Let me answer it briefly. And guys, if you don't care to know the answer, that's fine. But you're not the first person to ask, and I'd love to show you some of the work that other people... Are you going to the basketball game?
I think so.
Okay, that's fine. I'll show you later. So guys, the question on the table is, how is it that the increase in pH can be linear if pH is logarithmic? And the answer is because of the volume change. Yeah, fascinating, right? That yes, we are increasing pH as we're producing hydroxide, but, well, maybe we should say it differently. Yes, the pH is increasing as we're decreasing hydrogen ion concentration, but we are also simultaneously diluting the solution by adding more water, and the two work against each other to create a linear increase. I actually had a couple students about 5 years ago that got really excited about that idea and actually created a spreadsheet that tracked hydrogen ion decrease and tracked volume increase and tracked pH change and graphed all three. It's fascinating. I'd love to show it to you later. So, guys, what else do you notice? What do you got? Come on, guys. It's the glaring stuff. Shall we look right here? Yeah, let's talk about this. So, guys, you'll notice a couple things. First of all, when these graphs start to go vertical, the weak titration has a much shorter vertical component. And when it reaches that point, you'll notice that the equivalence point is not at 7, it's higher. Consequently, phenolphthalein is still a good indicator even for weak acid-base titrations. But an indicator like methyl red, and maybe why did they put that on there? Guys, methyl red is not an acceptable indicator for weak acid-base titrations because methyl red is going to turn colors when you're here in the titration, which is nowhere near equivalence. That's why we use phenolphthalein pretty universally, because it works for most titrations, whether they be strong or weak. You get the idea? Okay, so guys, here's then what we need to do. We need to now have the same conversation about pH initially, before equivalence, at equivalence, and after equivalence. So to do that, here's what we're going to do. Bump, 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 no, bump, bump. Okay, so guys, let's draw ourselves a weak, and I'll turn on the lights. Let's draw ourselves a weak titration curve. So we go like this, and let's be specific. So this is going to, let's not even do that. Let's just call it what it is. So let's go acetic acid, so CH3, COOH, and let's say 0.1 molar, and 0.1 molar, NaOH. Let's keep our players familiar. And then this is pH, and this is volume of NaOH. And our important points then are 0 on both axes, 7, I'm going to do that a little lower, 7, 14, and 50. And then, guys, we're going to say that we've got 50 milliliters of the acid. Am I doing okay? Okay, so then, guys, the thought is this. I think it would be worth, not 1 molar. I think it would be worth labeling pH 1. Why is that worth labeling? Because that's not the initial pH. It will be higher. So just pick some point higher. Only if you want it in your notes. Then, guys, from there, is 50 milliliters still the equivalence point? Is 50 milliliters of sodium hydroxide still going to take us to the equivalence point? How do we know? The molarities are the same, and we've got 50 milliliters of acid. So our equivalence point is still at 50, but where will the pH be relative to 7? Higher. So let's just sort of place a point somewhere above 7. And then, guys, how you choose to do this from here is up to you. If you want to put that little parabolic hump there, you can, but frankly, I'm not going to. So this goes up, and then over. What do you think? Bless you. Y'all okay? All right. So now, guys, we're going to have the same conversation that we had 48 hours ago about strong titrations, only now we're going to have it about weak titrations. So again, the 4-part conversation: initial, before, at, and after equivalence. So guys, let's talk initial concentration first. Sorry, initial pH. So how do we find the pH? And guys, think about this question outside the context of a titration. How do we find the pH of a 0.1 molar acetic acid solution? Icebox it, right? So guys, this pH is simply found, holy smokes. This is simply found using an icebox. Is that okay? Okay. Now, guys, I think for you to understand, we're going to make an interesting connection with the homework. In order for you to understand before equivalence, I think it's going to be helpful for you to understand the chemistry of what's going on here. So, in this before equivalent zone, you may want to join me in this. So, and I'm going to stick with red. So, here's what's going on before equivalence. We've got acetic acid, and that acetic acid is breaking into acetate ion and hydrogen ion. Now, before equivalence, but after initial, we are adding OH, right? Is that okay? We're adding OH. So guys, what we're doing is we are adding OH. And as we add OH, who steps up and reacts with the OH? The acetic acid or the acetate ion? The acetic acid. And it goes like this. And for every OH that we add, an acetic acid dies and becomes an acetate ion, as represented on the board. Does that feel familiar? Where have we talked about that construct before? Buffers, right? Is this a buffer? Well, it's not, because we haven't added the sodium acetate to buffer it, But we're not thinking of this as a buffer. We're simply describing the acetic acid being attacked by the sodium hydroxide. But here's the thing that's cool. The mathematical description of this is exactly the same math that allows us to study buffers. So guys, how would we study this process if we were talking about a buffer? What organization strategy would we use? An I-race box. And that's exactly what we're going to do here. We're going to figure out how many moles of these. Think through this with me, guys. We're going to think about how many moles of these, and then we're going to subtract, and then we're going to figure out how many moles of this hasn't reacted, convert to molarity, and do the equilibria. Does that make sense? And in that sense, it's an I-race box. So guys, we are going to study these with I-race boxes. Now guys, think about this. What is the math for the first two lines? Let's do this. What does the math for the first three lines of an I-race box look like? Moles, subtraction, and then how do we go to molarity? Divide by the volume. Guys, let's do that again. Watch my hands. What do the first three lines of the I-race box look like? Moles and subtraction, divide by the new volume, molarity. What did all of your homework look like that you just graded today? Moles, subtraction, divide by the volume, molarity. Guys, the math that you did, that you turned in today, were the first three lines of an I-race box. But why did we do it differently? Why didn't we do those calculations in an I-race box? Because there is no coming equilibrium to study because we're titrating strong things. So what we're going to do is we're going to do the same sort of math, but we're going to do it in an I-race box because in this case, there is an equilibrium that we then need to study. But it might be helpful for you to see the connection. You okay? Okay. Now guys, what about at equilibrium? It's not 7. So if it's not 7, what's going on? Well, what's going on here is the salt. How do I say this? A salt ion is reacting with the water. So guys, how are we going to study that? Well, we understand that that salt ion will be a weak electrolyte. It is the child of a strong acid or base, in this case it is the child of a weak acid, and therefore it's partially basic. But we'll study that using an icebox. But then guys, check this out. Are y'all caught up with me? What then do you notice up here? It's the same. Guys, after equivalence, it does not matter if the acid is weak or strong. After equivalence, all the acid has been consumed by the strong base, and any additional base that you add is just like dumping base into water. And so after equivalence, the process looks the same. You okay? Okay, so let's go back here, and let's go back here, and let's summarize. So here's what we know. Initial pH is found by an icebox. The pH before equivalence is found using an I-race box because the strong electrolyte is chewing up the weak electrolyte, and the pH is found by whatever weak electrolyte hasn't been gobbled up. Then guys, at equivalence, the pH is found by iceboxing the non-worthless ion in the salt, tearing water apart. Then the pH after equivalence is found just like it was in the homework we graded today. Is that okay? Now go look at your charts. So you decide if you like the way I wrote this, because guys, this is a summary of everything that we just drew into our titration curve. So initially, the pH is equal to the ion concentration of the original equilibrium. That's an icebox. Then guys, before equivalence, It's equal to the ion concentration of the unreacted stuff. How do we know how much didn't react? Well, it's that subtraction that's the top lines in the I-race box, but we're going to study this using an I-race box. Then at equivalence, guys, it is not pH 7, simply because one of the ions in the salt is reactive towards water, so we will ice box that reactive ion reacting with water. And then notice this is exactly the same as that, because after equivalence, all the acid's gone and it's just the base going into water. You guys good? Because now we're going to solve a few of these. I keep looking at my watch. Yeah, we got time. You ready to solve a couple? Okay, so here we go. All right. So guys, it says this. It says calculate, and this is again our same 0.1 molar solutions, 50 milliliters. We're starting with 50 milliliters of acetic acid. And we've added 45 milliliters of sodium hydroxide. Now guys, before you dig into this, and I know you'd like to write it down, and that's great, but what I'd like to do is I'd like to talk with you about some problem-solving thoughts before we get into this too deeply. You guys all caught up? You okay? So guys, the question that we need to ask and answer is this. Where are we? We've got 50 milliliters, right? 50 milliliters of the acid and 45 milliliters of the base. Did I remember that right? Okay. Where are we on this curve? Are we at point 1? Are we in region 2, region 3, or region 4? I just became right-handed. Guys, where are we? We're in region 2. We are before equivalence, but not at equivalence. So that puts us in here. So let's talk about the logic behind the calculation. So what's going on in this region? Well, we take a lot of acetic acid molecules and we bang away at them with sodium hydroxide. The hydroxide ions convert the acetic acid into acetate ion, and the pH is then determined by how much of this hasn't yet happened going back to equilibrium. It's again like a buffer calculation. So how are we going to approach this problem-solving process? With an I-race box. So with that in mind, this should work, hop back over here. And guys, let's make sure we can do this without having to look at the graph. Guys, how do we know just from the data that we're before equivalence? Good, that's the first thing you got to check. Same molarity. Guys, what if it's not the same molarity? You've got to do milliliters to liters, liters to moles, and figure out how many moles of each you've got. But because the molarities are the same, how do we know we're before equivalence? Exactly. We've got less base than we do acid, and we're putting the base into the acid. Is that okay? Okay. So guys, how are we going to structure our I-race box? What are I-race boxes always built on? What goes across the top? Which equation? Which chemistry are we going to make the heading for our I-race box? The equilibrium. Okay? We always start with the equilibrium. So guys, it's going to look like this. Our equilibrium is acetic acid in equilibria with its conjugate base. Yeah.
Don't need the first reaction to find the molarity.
That's what we're going to watch. That's what you'll see. You guys okay with that? Now guys, let me, I don't know why I never remember. Well, I do know why I never remember. I don't write out enough of these. No, that's not a C, that's an R. Where do I skip the space? After the R? Thank you. I want a little more space. I have a friend that looks exactly like that guy. It's really scary. Oh, yeah. Yeah. You know he's really good friends with Obama? The world's most interesting man. Yeah, he and Obama are like tight. I don't know why I know that. Anyway. Okay, so guys, let's now represent the chemistry that we're actually studying. So this is the chemistry of what's in the beaker. What? Oh, this is that acid. It's just written, so it's C2H. This is another way to write it. Sorry. Yeah, no, it's the same stuff. Yeah, sorry. I didn't even notice, because frankly, I copied this out of the book, and I just blindly wrote it down the same. Are you guys okay with that? It's the same acid.
I like power.
I do too. Yeah. So, guys, let's make sure we're clear. This is the chemistry that's going on in the beaker before we add any sodium hydroxide, right? So now let's add some sodium hydroxide. And we'll switch colors. So remember what we're doing, the way that we've chosen to represent this is by adding the OH. And then again, will that drive the chemistry to the right or to the left? To the right. So we're going to go like this. Yeah? So now we need to flesh this out with numbers. So in an I-race box, the beginning of the I-race box, which is again just like the math that you did last time, the beginning of the I-race box is the strong chemistry. And strong chemistry has to be in what units? Moles. So we need to know moles. And so guys, we do a secondary calculation where we go 45 milliliters, 1,000 milliliters is 1 liter. It's a liter. 1 liter is 0.1 moles, and that would be our NaOH. This always terrifies me, but did I do that right? Is that the right number of zeros? I don't know. That's why I'm...
Oh, yeah. Okay, yes.
Are we okay? Okay, and then guys, similarly, 50 milliliters, you can do that. Good? And that's the acid. Yes? Okay, so what does that mean? So we've got 0.005 moles of the acid. So going back here then, we've got 0.005. And I'm going to be horrible with significant digits. We've got 0.005 moles of this. We've got none of this. We've got none of that. Notice that difference. When you've done I-race boxes before, we've used them to describe buffers. And when we have a buffered system, you would have excess acetate ion as well. In this case, we just don't. But that's okay because we're always going to be adding a base to the acid, so we don't need any base ion to take on the acid because that's not what we're doing. Okay, so now we do the reaction. And we are adding 0.0045 moles, so 0.0045 moles of base. Will we add or subtract that number from the concentration of the acetic acid? Subtract it, because that's what's being consumed. Then similarly, this will be created. And what about the hydroxide ion? Untouched. Or not hydroxide, sorry, hydrogen ion. Mm-hmm.
Why does the OH cause it to create hydrogens with the hydrogens behind the OH?
It does, and it makes water. That's the whole point. Yeah, it doesn't change.
Saying that the hydrogen
No, we don't represent it, but the side product, if you will, of this is water. Yeah. Okay, so now, guys, we need to do that math. So 0.0005 and 0.0045, but then, oh gosh, this is moles, and then we need to divide by the adjusted volume, 0.095 liters. Okay? Well, it'll probably be just as easy for me to do this.
And we don't have to include the water that's created.
No, it's negligible. Guys, I'm just going to do that. Is that well, I'm just going to leave it at that. We're worried about process, and this will cut down on clutter if I get ugly with sig figs. And then, guys, this is 0. So now we understand what's left in that solution. We've got a little bit of unreacted acid. We've got a fairly significant amount of created conjugate base. And now these new conditions need to go to equilibrium. So down by x, up by x, up by x. So this is 0.0053 minus x, 0.047 plus x, and x. And then, guys, I know you're going to find this wildly unsatisfying, but do we need to solve this from here? Can you picture how this is going to play out? You're going to write the Ka expression. Your plus and minus x's are going to cancel. You'll simply do that division, then move that over to the Ka side, and that'll give you x, and then take the negative log of that to find pH. Yeah.
How is this any different from the stuff we were doing earlier?
It's not. That's the point. Yeah, so the only difference, so where did we do I-race boxes before? And the answer is we did I-race boxes before studying buffers. And when we were using these to study buffers, the only difference is we had an initial concentration of that from adding the conjugate base salt. But we don't need to worry about it in this case because the very definition of these titrations is it's a weak acid and a strong base. You wouldn't take this and then add a strong acid to it because acid to acid doesn't do any chemistry, and we don't have a concentration of that. So it's the exact same math, you just don't have an initial concentration of this. And that's frankly why I like to teach it this way, because it brings you back to a process that you're familiar with. Go ahead.
Okay, so like when you add the OH to it, you know how the
Mhm.
yeah.
Yeah.
Like why do you not count that as the hydrogen? Like that's so
Why don't you count it what?
like as a hydrogen.
You mean this hydrogen?
Yeah.
Because it doesn't, and that's what Matt was talking about. So the idea is, so you're comfortable with the idea that we've got our vinegar, our acetic acid, right? And so we add OH to that. So what chemistry takes place? Well, the OH, as an aggressive base, steals a hydrogen from the acetic acid. When this hydrogen gets removed, we're then left with the acetate ion that's this, but where does the hydrogen go? Well, the hydrogen bonds to the OH and turns into water. What it doesn't do is release hydrogen ion into solution because that hydrogen gets tied up as water. Okay, then once all of that's done, which is described up to here, once all of this chemistry has taken place, then these new concentrations of acid and conjugate base ion, then they go to equilibrium. And it's at that point that we start seeing the production of some hydrogen ion. Correct. That's right. Yep, go ahead.
How is the hydrogen ion produced at equilibrium? Is it like the water breaks up?
No, so it's the breaking apart of the acetic acid. So
Oh, that's still happening.
it's the acetic acid that's unreacted, then falling apart and making hydrogen ion. You guys okay? So guys, here's what's going to happen. We have to look at this next problem solving process or your brains are going to explode. So we are going to bleed into the break. At the end of that time, if you're going to the game, go check out, do your thing. If you're not, we'll all just leave. If you're not going to go to the game, come back for third. If you are going to the game, go check out, understanding that I have to mark you absent and then you sort that with the attendance office. But guys, you've got to see this. This is unlike anything you've seen. It's crazy. Ready? Calculate the pH at the equivalence point. So guys, what do we know the pH isn't? 7. This gets nutty. For those of you that are already organizationally challenged, this could be crazy. So let's do this. Before we start trying to come up with a problem-solving strategy, what I'd like to do is remind you of the chemistry. Please don't write this down with me. Not because it's not important, but because we're going to write it down again in a more organized way. But let's just brain dump the chemistry. So guys, here's what we've got. We've got our, whoa, I do not like that. So guys, we've got our acetic acid, and we know that that's breaking apart into acetate ion and hydrogen, and we're adding OH. Familiar. So when we add, let me say that differently. When we're at equivalence, what has magically happened to this system? So what does equivalence look like? When we reach equivalence, what do we know about the amounts of these two things? They're equal. So guys, at equivalence, that process that's described by those two arcs, those two arrows, guys, this process is all done. We have added exactly the same number, moles. We've added exactly the same number of these as we started with these. So all of this is gone. Gone. How much extra this do we have? None, because we stopped titrating exactly when it turned pink. So all of this is gone. We don't have any extra of that. So what do we have? Well, guys, we've got this. We've got acetate ion. All of that acetic acid has been converted to acetate ion. So what does that acetate ion then do? Well, that acetate ion then reacts with the water that has always been present in the system, and we end up with this chemistry taking place. So this is the chemistry that we need to study. At equivalence, we don't have any of this stuff. At equivalence, we've got that stuff. And that's the chemistry that determines the pH. So we need to figure out how this attacks water, because that determines the pH. Is that okay? Because guys, if you understand that, I need to ask you a difficult question. But do you understand the concept or the chemistry? Okay, so let's say it one more time. At equivalence, this is the chemistry that we need to study. Because how much acetic acid is there left? None. How much OH is there? None. The only thing we've got left is the acetate ion, right? Here's the hard question. How much acetate ion do we have? No. Let's ask it generically. How much acetate ion will we have at equivalence? Let's say it again. How much acetate ion do we have? What's the answer? how much acetic acid did you start with? Does that make sense? How much acetate ion do you have? Answer, how much acetic acid did you start with? Now, how do we know how much acetic acid we started with? Do the math. We know the volume in milliliters. We can convert that to moles. So if we can determine the number of moles of this that we started with, we then know the number of moles of this that we have at equivalence. Let's say that again, because that's the thing that makes this hard. Guys, how many moles of this do we have? How many moles of this did we start with? Because all of this has been converted into this, and so we need to know how many moles of this we've got. So we need to know how many moles of that we started with, and we already know how to figure that out because we know the volume, and we just go milliliters to liters and liters to moles. Do you get the idea? Then, guys, what we do is we take that amount, and that becomes one of our data pieces. Once we convert it into molarity, it becomes the data piece in our icebox. Questions about the concepts? You ready to do the math? Okay, so here's how this goes. Here's what you're going to do. We're going to set up our icebox first. Don't write this down with me, but I'm going to just give us this. Guys, I'm going to give us this as our foundation, because that is the chemistry that we're studying. And then we add OH to this, and I know this is hard to see. We add OH to this, and that's the chemistry we're studying. So based on that, what are we going to icebox? Well, we are going to icebox, and you can do this with me, the conjugate base ion attacking water. That is the important chemistry at equilibrium. This is gone. This is formed. That's the point behind equivalence. So guys, the important chemistry then is that conjugate base ion attacking water. And when it does, our products are acetic acid and hydroxide ion. And guys, what we're going to do is we're going to icebox this. So now we need numbers. I don't know why, but this always just makes me really happy. I love that squiggle because it's one less thing I got to think about. So guys, now we need data, right? What kind of data populates an icebox? Moles or molarity? Molarity. All right, so now we need some molarity numbers, right? So molarity is moles divided by liters. So we need to know how many moles and how many liters of this. But guys, let's do it logically. How many moles of this do we have? How many moles of this do we have? How many moles of that did we start with? Does that make sense? How many moles of this do we have? How many moles of that did we start with? So let's figure out how many moles of that we started with. So guys, we started with 50 milliliters of the acetic acid. 1,000 milliliters is 1 liter. 1 liter is 0.1 moles. So we've already done this math. 0.005 moles. We're just going to keep going. We've got 0.005 moles of acetic acid. But we need that to be a molarity. So we need to divide by volume. So guys, what is our volume at equivalence? 100 milliliters, 50 of each, right? Because we started with 50 milliliters of this, and because the molarities are equivalent, we also need 50 milliliters of base. So our volume will be 100 milliliters or 0.1 liters. So our molarity is 0.05 molar. Did I do that right? Oh, good. Okay, so coming back over here, 0.05 molar. This is 0, this is 0. This goes down by x, this goes up by x, this goes up by x. So then we have 0.05 minus x and x and X. We okay? So now what do we do next? But what kind of KC expression? KB. So KB is equal to CH3COOH and hydroxide, and on the bottom our conjugate base ion, which is acetate, not the water. Now guys, we got a problem. What's KB? We got the Ka for the acetic acid, so we can go Ka times Kb is Kw, and we can figure out the Kb for acetate ion. So so Kw is equal to Ka times Kb. You'll probably be doing this down below. So 1 times 10 to the negative 14th is 1.8 times 10 to the negative 5th times X. That's a mess. So 1 times 10 to the negative 14th, and then 1.8 times 10 to the negative 5th, and divide. And I get 5.6, again being horrible with significant digits, times 10 to the negative 10th. So 5.6 times 10 to the negative 10th is equal to x squared all over 0.05 minus x. Heaven knows we can drop the minus x, because that would be a 10 to the negative 10th. So we have x squared all over 0.05. So we have 5.6 times 10 to the negative 10th times 0.05. Take the square root, which apparently I can't find my, there's my square root button. And I get, so 5.3 times 10 to the negative 6. Do you buy that? Not yet. So 5.3 times 10 to, is that right? Is that number right? Am I okay? So then guys, what do we do with that number? Well, we go POH is equal to the negative log of OH. Plug that in, find the POH, then pH plus POH is 14, and then find pH. Is that okay? Okay, go ahead.
What is the value of KW?
1 times 10 to the negative 14th. Yeah, my board is having a hard time writing in that upper corner. Walk, not literally. So guys, here is your homework.